This is a new talk, right? These are new, relatively new things that we want to explore in the near future, and I'm not exactly certain that I've got the talk really polished or exactly how long it takes. So ask questions, and I'll adjust the timing and everything else. We'd love to people to talk and ask questions and say, that's interesting when you think about this, or I'm confused, or whatever else is going on. It would be great. Thanks, Elena, for the intro. I'm a principal engineer at NVIDIA now. It's been a little bit of a journey to get here across Amazon and ending up at NVIDIA early this year. But NVIDIA has been very supportive and seemed very positive about, let's go there, Quincey, work on HDF5 probably for a while. We might even get it installed. So I think I've got good chances of exploring most or all of the topics that I'm outlining here, probably in the next year or faster if they do give me some help. It'd be really nice. So we'll talk a little bit about, open ideas in the HDF5 space, right? And of course, but and then go over these three that I think are both relevant and possibly overdue and valuable for the communities that we currently have. So obviously this talk, we're gonna hit accelerator native I/O. I mean, GPUs and other kinds of accelerators have like majorly taken over the HPC space and then well beyond, right? Completely well beyond that. A form of sharding HDF5 files that should allow us to expand. And this is one of the places where it's really overdue, I'd say, into object storage and exploit that out into the cloud, which is why it's overdue. And streaming, we've explored a little bit, but I'd like to actually get some code down and actually get some users on the new code that would accelerate their use of HDF5 in some really significant places and ways. There's a lot of other things that are really obviously visible on the horizon. It'd be great to do queries in HDF5, especially if you could like cover, hey, I've got this million HDF5 files. Could you please tell me which ones are like this? Security, oh my gosh, I spent 2-3 months last year at Amazon doing nothing else but closing CVEs. The 30-something or another that Dana mentioned yesterday, that was principally work that I did, picking up squirrels inside the library and going, what the heck is going on? Why is this corrupting memory in this funny way? Why would you ever do that? And boy, did we write that. A few thousand lines of go fix that. Data warehousing probably goes to query and indexing, but we need to be able to manage these large collections of HDF5 and other data sets in good ways. Thanks. CPUs, data processing units, are on the horizon, and hey, they're going to actually give us some silicon that we can actually use as storage keys, right? So that would be very cool. It's not near enough term that we're going to write code against it soon, but that would be very cool. Obviously, cloud native storage, which we're like overdue on doing a real cloud native solution. CS goes a certain amount. Reading S3 goes a certain amount, but I think we need to go much further and really, really be first-class citizens in those spaces. And we've played around trying to figure out how to get concurrent multi-process access, and that's an obvious thing. And I think some of the sharding storage that I'm going to talk about today could play out in that direction as well. But it's probably going to be next year, or maybe a little further, or maybe the same. Hopefully, somebody else here goes, gosh, that's really cool. What do you think about whatever, right? So, and picks those up, and it starts to like work on this thing. So dive in on the accelerator native storage. I'm being generic here, right? Because although I work for NVIDIA, we are contributing to an open source package. Jensen Huang, the CEO of NVIDIA, is super excited about accelerators. He's a great guy. But he's really saying accelerated computing is dramatic. It is speed up over general purpose computing in every single industry. I kind of mentioned this, it's really obvious. If you look at the industry, we used to think, we have the biggest, fastest supercomputers in the world when we deal with HPC. I'm sorry, man. That is a tiny, tiny, tiny percentage of the machines that are being deployed as AI clusters and other kinds of machines out there. They're more powerful, and there's a lot more of them running around out there. We better start paying attention to these accelerator workloads. Otherwise, it's going to be impossible to keep HDF5 modern relevant in this new era. So one bit of background here, because I'm going to talk about it. HDF5, you all know, right? Just to kind of frame the problem. We define a data set as conceptually a multidimensional array of elements, right? And when you store it in HDF5 files today, it's either contiguous as one big block of all the elements together, or you break it up into chunks. Just still all the elements. You didn't save any size, but you probably are saving time when you do access to those chunks. And if you want to actually make it smaller, you have to make a chunk. And you get space and possibly time savings for chunk storage, right? So just going to use those techniques a lot. Because AI techniques are really leveraging, as they keep saying to me, and the messages I get is, hey, we really want to load your HDF5 stuff and do training and inference on it, but it's all compressed. And by the way, could you fix that so that it goes faster on these accelerator machines? And the techniques I'm going to talk about here apply to non-compressed stuff, but it really works nicely for compressed things as well. So this is cartoon level. This is what a GPU node looks like, right? There's one or more CPUs on the node to one or more GPUs on the node. They're connected in some way with a bus, PCIe, high-speed thing. And most of the time, NVMe sitting on the bus too, if you really want a high-speed node with high-speed data access, something like that. Otherwise, it hops across the network to something like Buster or something else a little bit further away. But fundamentally, the GPU can talk to storage, CPU can talk to storage, and they're all close enough on the hardware that we can do interesting things. But today's world is kind of crummy with CPUs. The GPU goes, hey man, I need some data. And the CPU goes, yep, right? Because HDF5 runs on the CPU. And it talks to storage. And it says, hey man, I need these chunks. Give me these chunks. Okay, fine. Here's a bunch of compressed data. It's a bunch of chunks. Then, because we're still in CPU land, the CPU is nowhere as fast as the GPU at like core computing techniques these days, right? It sits there and it runs the I/O filter, decompressing chunks in CPU memory very slowly compared to the GPU. And then it has to transfer them all from CPU memory onto the GPU. It does that. On the CPU is slowing the world down. Typically, let's just say the chunks are 2x compressed, right? So when you expand them, you get twice as much data. Just ballpark. Not a great compression algorithm. You ran gzip on it, it's fine. So 1x of your chunks, your compressed chunk size, transfers across the node bus, right? To get them into the CPU. Then I sit there and spin the CPU a bunch, and I expand them in CPU RAM. And then I transfer the expanded version of the uncompressed data onto the GPU. So I'm transferring 3x of the compressed version across the interconnect, right? 3 times the amount of data that we brought from disk is going across the interconnect bus. Could we fix that, please? What would we do if we had a more GPU-based pipeline? Can't quite get the CPU out of the picture yet, but if the GPU says, hey, man, I need some data, CPU can say, you know what? I want you to talk to him. I don't need to be in the middle of all this. So the CPU can tell storage, just transfer the compressed chunks directly over onto the GPU. DMA these guys directly over from storage onto the GPU memory. Then I can run, CPU says, I got them there for you. Please go ahead and run the multi-threaded hardware accelerated, not just running on the GPU, but there's actual hardware acceleration chips, components on the GPU chips that decompress at line speed of, high bandwidth RAM in parallel, all those chunks. Bam, they're done. Now the GPU can get going again, right? We did a third the amount of transfer over the interconnect because we just moved compressed data where it really needed to go, the end game. And then we used the hardware accelerated GPU in parallel multi-threaded algorithm to go decompress the data right where the GPU needed it already, and it's good to go. Huge savings, huge amount of bandwidth. All right.
So I'm guessing this would typically GPU direct want to do on any kind of things. It basically assumes that GPU streaming comes while the data is coming, right? It's not doing any other job.
Right.
But most of the machine learning algorithms, at least, would be doing some computation in parallel. So it's basically the CPU not doing anything, and we have a lot of memory. So that's why typically they pay the protocol that transfer, assuming GPU has enough job to do it, and it's enough compute intensive to hide all that cost happening in the behind. So my question to you is, what are the use cases, practical use cases, applications that I've seen? Because I have not seen yet any. Like I've looked at GrowMax applications, which are very GPU intensive. Looked at AI, a lot of workloads. All of them are typically enough compute power that you hide all of the. I agree with you. This is just unnecessary like copies all around, but it does not matter because it happens while GPU is already doing something, and you don't want to offload something onto GPU and stop it from doing its work while CPU is not doing it. So I would like to know more about this.
Yeah, so Harry's mentioning a case where, the CPU is kind of essentially an available resource that you could just, yeah, fine, go up and I don't care how slow it really is, go do the decompression over there. And that's really valid, right? But it does take a certain level of sophistication and you've got to be able to pipeline it. The GPU's got to be able to indicate that it wants the data to be prefetched. And this is sophisticated, I want to get my kernels to work this kind of way. Hardware accelerated decompression happens literally at the speed of memcopy. So there is no overhead for doing decompression on the GPU. It is just blindingly fast. It's probably faster than.
This thing moves the compressed chunks, even if you wanted to use the CPU depipelining,
right.
Move the compressed chunks directly to the compression.
Yeah, the overhead of moving the data around and creating noise on the interconnect is not worth it.
Most of them are connected to PCIe,
right.
Which is most of the case.
Most of the case.
Then moving things from the storage, no matter how fast it is, could be slower than moving the data pretty ready with everything moving faster on the CPU. So again, assuming you have
storage is on the PCIe bus as well, right? So there's no.
Consuming the data in the GPU, but moving
No. You'd be like, look at an actual service.
Somebody's going to run away.
Like you have more memory bandwidth than the PCI bus by a factor of 2 or more than you have the DRAM. DRAM is basically it's a bus you turn around. You actually have more bandwidth in the modern server through PCI storage than you do your main memory. Look at the most recent AMD server stack. Yeah, just go look at it online. You will be surprised. There's more PCI bandwidth to storage than there is main memory bandwidth to DRAM. The only servers more memory bandwidth are the ones that are HBM, and those are the only info I can bring out. Those are very low.
But either way, my point is at least the evaluations which are there out there on HPC machines still show that you get a lot more parallelism out of memory than you would get directly out of storage.
Not if you find new box. You're talking about new stuff. Like, if you buy a new piece of equipment, like, go to Andy's website, look at the server chips, Intel, look at the ratio of bandwidth, the PCI is unidirectional, get both ways. And compare that to compare it to anything through edge memory. Game over, there's way more bandwidth on PCI. It's very counterintuitive.
Okay, I gotta go.
Sorry.
No, that's fine. Thanks, Temple. Yeah, no, I mean, we can trigger this, right, from the GPU and get the data in there, but it's just so much faster. It is just amazingly, blindingly faster on the GPU to get the decompression over there. And save the bandwidth.
PCIe through storage is much faster than.
It's a direct DMA out of your NVMe. Yeah.
Moving data from the RAM.
Yes. Yeah. It's crazy fast. And then crazy fast on the GPU. Almost got there. All right, so in HDF5 land, what do we really need to do, right? We do the I/O with POSIX balls today, right? The dataset chunks are cached wisely, I think, but they're in CPU memory. The I/O filters run in the CPU, and they access those chunks in CPU memory, and then we got to transfer it, right? Another walk across the PCIe bus. And so, clearly, these are the steps we're doing today, right? Running all this and then passing it over. A whole bunch of extra computational work that we're doing in data movement work. On the accelerator, we can switch this over to GPU direct storage. And I'm definitely going to make this framework flexible and agnostic, right? I work for NVIDIA, but I'm contributing to open source. It has to be able to handle AMD chips, Intel chips, whatever anyone else comes along, Google Tensor chips, whatever. So yes, today I would be deploying a GPU direct GDS VFD to do the I/O, and I'd be doing hardware accelerated things. This is all pluggable in these kind of components, in these kind of ways. We're going to move the chunks directly into GPU memory, like I said, and the I/O filters, they're already pluggable, right? Very easy. You just say, hey, the hardware acceleration is connected to this buffer, just click, go. It's very simple. And so in the GPU, we're going to step through the same, ask this CPU to initiate things because we're not quite there yet from the GPU world. It's going to do GDS direct into the GPU like we showed. Click on the I/O kernel, and it's going to use the hardware accelerated and decomp, the compression that runs on NVIDIA chips today. And we're all done, right? All this happens in a mind speed practically. So what are the library? What are the software changes we need to do this? It's fairly straightforward. We've already got a VFD interface that's pluggable. We need a little bit of flags to say, by the way, I want you to put this over here and you can demand over here in the GPU memory, and that's good. Let me know if you can do that. So maybe a couple flags in the virtual file driver interface. We need to update the chunk caching code. This is probably the bulk of the work, not only because the chunk caching code is moderately crusty and old and weird, but it's got to be able to be pluggable enough that it can store its cache data on the GPU as well as on the CPU in some modular way. I'd like it to be able to cache off and hey, there's this very fast NVMe or whatever else storage there too. But we'll see. And then obviously, filter interface is critical. And it's got to have at least another flag or two that says, my source and destination can be on the GPU in order to do this kind of compression. Wonderful thing about this, how the applications need to change. They don't. Because library, there's already calls that ought to detect the buffer pointer is residing in GPU memory. So if you give me a dataset read call and the buffer pointer, I can look at it and say, oh, that's on the GPU. I should invoke the GPU direct native I/O pipeline, click, 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 compose my pipeline in an optimal way, then boom, it's out the door, right? And in the future, we should be able to deploy the GPU over in front of the storage component of this, and then we'll be able to actually offload all kinds of interesting things directly on top of the GPU. GPU can contact it directly for the I/O request, the CPU can get out of the picture entirely, and the metadata cache and other small little bitty things that are happening here that we would normally have to keep resident on the, sure, you want to try? Good, that'd be great. I can walk around more. Can you patch me in quickly? Okay.
I will ask the question, how portable this solution will be, and how much room do you need to having filter functions to enable it?
Sorry, it's strict.
Question.
No, I didn't.
Okay.
I was trying to-
Okay, the question was how portable what you're proposing will be.
Well, that's why I want to make it, clear. The question is, well, is this hardwired into NVIDIA? It clearly can't be. It's already got two components that are already pluggable and easily modular, right? These are already pluggable and you can replace one with the other. If we add a capability flag to the VFD that says, oh yeah, I understand how to drop things into accelerator memory. Easy flag. It's not specific to anyone in particular. Same with the filters. The only thing that's a little tricky is we're going to have to modularize chunk cache enough that probably some form of dynamic loading can happen to say, I have the caching component that understands this kind of GPU memory. But again, modular, right? So that we can accommodate Intel and AMD and NVIDIA and everyone else. So I think all of this is pluggable. CPU, I don't know. That's more than a year away. I don't even think about it. And I got the CPU. It's sitting around now. What am I going to do with the dumb CPU? It's just sitting around. Maybe I build indices, track performance, do logging, do weird stuff. Give it to somebody that's like, I don't know what. CPU might be redundant eventually in this kind of thing. But
It's your PCI switch.
yeah, something. I don't know. But anyway, it's far enough in the future. I don't have to think about it. Okay, so okay, on time. So. Any other questions, or we'll jump into the fun object sharding and fun things?
I quickly looked up the NVIDIA. They are using 16 NVMe's over different PCI playing 16 cards.
Okay.
Compare against 4 RAM slots they have, essentially. So, and then they match performance. So,
Okay.
I've run these benchmarks myself, and then I'm 100% sure at least on Frontier and on this PC machine, this has never happened. If you are doing a fair comparison with what you have in terms of even 4 NVMe devices, you want to pass, you're not going to get. I'd love to know later on.
Okay. Yeah, I might be tainted.
Can you tell me the use case?
Well, I might be tainted with internal knowledge of, I know that we can do the compression at line rate. Yeah, so it is no more expensive than a memcopy and probably faster.
So I took that. No, that's great. But my question is, what applications do you see in cloud world or HPC world where this could be potentially?
I'm literally not certain that the cloud world and the HPC world are going to leverage this. It is really at scale inferencing and training on, say, climate data on a massive bank of Blackwells or something else modern from NVIDIA and other people, right? So it's, like I said, HPC is really market share in the two world. Your skills up to date, people. So, yeah, I'm happy to chat more. Maybe I'm wrong, but I have a good sense.
No, I completely agree that the technology is important in the context of HDF5. In the last 3 years, I've been struggling to find good use cases where I can say that, okay, CPU can twiddle thumbs, not do anything, and let's move everything to GPU directly. In most cases, it turns out, make use of GPU, move things into memory, move it from there.
Yeah.
That's why I'm curious more than anything else to find them.
Yeah. The CPU maybe, instead of twiddling its thumbs, like we were saying, becomes the orchestrator to make certain that the optimal pattern is happening. It's like, oh, right now, I think the right thing to do is move this compression over to the GPU, and right now, maybe I'll hold it on the CPU and I'll do it here. And it takes over that.
There's other use cases, right? Certain algorithms are still not optimized for GPUs to do pre-processing,
right?
Or AI training and inference. So those are again great use cases where you don't want to direct GPU purely because not everything is optimized.
Yeah, I can tell you a story. I can tell you a story about parsing CSV on the GPU. So, all right, I'm going to go. Thanks, man. Sharding, right? And this is kind of a catch-all for how do we break up HDF5 files in useful ways that accelerate performance and could be applied to both on-prem object storage systems, Deos could be an example of that, and cloud storage systems, and it works just fine, as we found out with ZAR, in local POSIX file systems as well, right? So the HDF5 file format today is, well, it was built and optimized for primarily, right, high-speed POSIX I/O, self-describing, it lays things sequentially, you know, byte by byte in the file. Asterisk on a single file, yes, we've toyed with other, you know, we could do split files and multi-files and some other mechanism for breaking this up, like subfiling and things like that. But fundamentally, the whole native all connector now thinks about things as a giant serial file and how do I make that work. We wrote lots of custom code to do file data structures, right? And fundamentally, it's storing blocks of contiguous elements. Spoiling a lot of the fluff around the edges, important fluff, but you know, other things, this is core what's going into the file format. Right at the beginning, right? This was almost the mission from the get-go. Make this work with NVIDIA. And we compensated, particularly based on the machines that were available. We required implementations to perform like the data so that it makes you handle the when cloud computing came along in 2006, basically avoided it for 10 years. We did not pick it up. We looked at it and said, that's neat. I wonder what the cloud computing world is going to do. Is that going to succeed? Yeah, I wonder why. That's the thing. We got a lot of HPC work to do. Let's keep doing that. And finally, we started, you know, thinking about finding ways to compensate, right? Again, right? HSDS, one of the important projects at the HDF group, addresses this, right? It's cloud hosted, it has JSON configuration bits and pieces, it has its own servers that run natively on the cloud, and that's great, it does a wonderful job of doing things, but it didn't go all the way, fully native, in my opinion. And we have these cloud optimized HDF5 access with read-only S3s, still a native file format, but you just took the POSIX file, shoved it into the cloud object, and then how can we optimize access to that? Great, that's cool, but it's compensation. It's not native, right? Now, just take a look at somebody else besides Jay and Scott Klasky who were frustrated with some aspect of HDF5 and decided to do something new, you know, bizarre people, right? So ZAR has a lot of the semantic model that HDF5 has. It's missing some of the edge pieces, but it's a hierarchical group of data sets as leads. Fundamentally, core pieces are, they're not new, right? It's a nested set of groups. It doesn't have fun linking. This is kind of some sophisticated things that we do, and they add their own stuff. But it stores things in the file system. It does very little metadata management of its own. There are no B trees. There are no keys. And none of the other stuff that we write, right? It stores things in the file system hierarchy and uses JSON for storing the metadata, right? It's just, here's some text, right? Here's a description of your metadata for this particular object. And then, instead of writing a B tree and doing chunk lookups, chunk indices, it just shards the stupid stuff and stuffs it into chunks go as files in the file system, and we use the file system as the B tree and the chunk index, and we do everything by names in the strings, right? So like, oh, clever. I wonder if they're going to leverage the file system well enough to make that work. And by and large, there are some huge use cases where this is a good idea, and they get some real leverage out of it. It particularly can apply well object storage in the cloud. And boy, have I got a lot of feedback from people in NVIDIA like, ZAR looks really cool. Are you sure about this HDF5 thing? And they've got good use cases that say, this is like twice as fast, 5 times as fast, 10 times as fast. It's like, well, we better pay some attention, or they're going to eat our lunch. So I like Jay's topic and title from yesterday. We're going to rebase for the win, right? How can we redo this so that we keep the API, because that's what people are programming to, and make their applications change as little as possible? What do we want to do? We need to target all 3 now. POSIX file systems are really important. They're probably never going to go away. But wow, there's a lot of object stores running around. And because the modern world of object stores runs on S3 interfaces, even for the local on-prem stuff, you can take the same technology and immediately take your on-prem solution for an object store and apply it to cloud storage. One step, you're done. Basically, just go over this network in a different way. So we need to keep the data model concepts, right? These are really critical. People thinking about what HDF5 is. groups, data sets, attributes, links, data spaces, data types, these kinds of concepts have to get translated appropriately and still be as fully robust, as featureful as we provide today. Got to be self-describing enough, hopefully a little bit nicer. There's places where we can't bootstrap a specialty VFD in some ways that I'd like to fix. And of course, scalable I/O array data, core essence of the performance and the user base that we have today. We can leave behind stuffing all the metadata in the same file. Talk about more. We can also not write 2 versions of B trees, 3 heaps, and like all kinds of key value lookup pairs. Do need to also add in the sharded data storage, and let's replace all the stuff we're tossing out with all these custom data structures with a professional outsourced solution. We're going to use a database for metadata. Let's take the professional. So obviously we got to keep all these data model things collaborating a little bit. Got to do the self-describing format. We got to make it bootstrap in a nice way, and it's got to be able to, be portable and archival and all these good things. And of course, the second by none of HDF5 is we're keeping the array access and figuring out ways to make that even better than it is today. Holy cow, was it a bad idea to mix the metadata with raw data? Like, I don't know how many twists and contortions go on in the HDF5 library today that are just trying so hard to make my mistake from 25 plus years ago of mixing all the metadata in with the raw data and fixing that. It might have been fine if we just done page block size I/O of a block of metadata, but no, we decided that 576 bytes was the right size for the starting size of an object header, and that's what we're going to allocate in the file. And boy, did the world not need all the data structures we wrote. They were fun to write. They're cool. I like computer science and creating new things. We should have put our energy somewhere. We got to do this. We got to figure out what the wins are for ZAR and meet and exceed those. We got to say, that was a great idea, and we did that better. A lot more friendly to the object and cloud storage, like I said. And let's give it up. We're just going to go find a professional solution that does the B trees, page I/O, caching, all that, offload the dumb stuff, right? We waste so much time and effort fixing the, whatever piece of the metadata flow in HDF5. And it gives us the capability to query and index and stuff, so that I get these complaints. Now, I'm much more exposed to them now from software vendors that say, I got this HDF5 file, and I got 50 million HDF5 files. I just want to find a stupid one that has an attribute named foo in it. And I got to parse the whole stupid file, and I got to custom create these queries out of programming. Could you please figure out a way to make this go faster? So yes, I'll give you a database. You know how to use a database, right? And when we have a database, it can be local, like an SQLite, right? So it doesn't have to be scary technology that you have to license. There's great open source. Actually, SQLite is weirdly in the public domain. And you can go into the cloud very transparent. Same technology. People are used to it. So what does this look like, right? Playing around on the Mac, I discovered, hey, these apps that we think of as apps, when you double click on the icon on your Macintosh or somewhere else, they're actually directories with this whole fire system built inside, where does everything go inside the bundles inside Mac applications. So let's steal that technology, right? We're going to create bundles where a directory is equivalent to an HDF5 container. This is not rocket science, right? Really easy to detect when you open. If you get a name and that's a file, it's a native file. Boom, we go do that. If it's a directory, must be a bundle or somebody made a typo, right? But if you give me a name that's a directory and I look it up and I say that's a directory, I'm going to go look for the bundle keyword and find the bootstrap piece of that. And if it's there, I'm going to treat the whole directory as if it's an HDF5 container. Really, really, really simple. Obviously, another property in our 600 plus edition of property lists to say, I want to create a new bundle container. Opt in for that, because when you give me a name, trying to create a file or trying to create a directory with a bundle, still need to opt into that. Obviously, bootstrapping is still necessary. We got to do the self-describing, but we're just going to take this R solution, right? We're going to stuff a JSON file and it has a magic name inside the directory, and that's what we look for. And you go, oh, hey, great, there's a JSON file with the right name in this directory. It's the superblock. JSON's great. I don't know if it's going to survive for 30 or 40 years. Like, probably will. You can always replace the bigger, it's fine. Pretty easy to read, self-describing. If you need to, have a connection to a cloud database, you can tell me what the URL is, what the configuration is to go get to it, or hey, that SQLite file right there, that one's your metadata file. Pretty easy to do, all bootstrapped out of a superblock JSON. The metadata stuff, I haven't got far enough into this to really figure out what the schema looks like for the tables and stuff in the metadata database, but maybe a table per group, storing all the links, just key value pairs. Table per object for the attributes, right? They're also key value pairs. What do we do about the object metadata, dimension, storage layouts, and stuff like that? I don't really want tables and stores, key value pair things in the database. Maybe we go with NoSQL like HUG24, or maybe we go with SQLite, or maybe we have two. I don't really care, right? Two metadata files would kill us. And let's leverage ZAR. Let's go one better than ZAR, right? We can actually aggregate multiple data sets in one file. If you've got a million tiny little data sets, I'll shove them all in one file. Great. We don't overload the file system. We don't get the massive overloading of file names and everything else that goes into the directories on Lustre and kills all the inodes from ZAR. We can do that aggregation, right? We can do the sharding, same kind of technique, right? We can use subfiling and actually create subfiles that are much more sane to look at and actually leverage the underlying file system in a useful and meaningful way. And it's just a different kind of way of doing chunking and lots of things, right? This opens up some very nice theories for us. How do we get there? We're going to extract more guts out of the native vol connector, right? Anything that would be common across connectors. Because there's a whole bunch of stuff we left in there, right? And like, we don't want to do the work right to extract that or make an API around it or whatever. So we're going to either leave that in the main HDF5 library, move it back with like the same kind of place that property list and ID manager and stuff reside in the library. It's not connected to a single vol connector. And that native vol connector will get even smaller. Just the knowledge about the file format specifics, the native file format, and how to deal with that. All the idea about chunking can get abstracted out into a chunk component, and yeah, that can get used by native vol connector and other ones. Obviously, we're going to write a new bundle vol connector, use the file system as an object store. Makes it very easy to transition a bundle from your file system to an object store to the cloud, because it's already sharded. It's already there in your file system the way it needs to be in the cloud. Just shove it over there. Like I said, put the metadata operations database, want a pluggable interface, interface within this bundle vol connector so that we can do multiple kinds of databases. I want to have SQLite, DynamoDB, whatever else. Have it, do whatever you want in terms of talking to your optimized metadata form of things. And really, it's going to own the knowledge of how is the sharding happening for data sets. And then it falls into the IO core that we extracted from the native vol connector and share between these two vol connectors and maybe more that makes sense. So very fast, I'm trying to get my time filled and be on time. I think we can get there. I think we can meet and exceed, right? Because this JSON for all the metadata, no matter how many objects you have that many JSON files to go pick up and parse, right? And it's just crazy thing, right? So we fix that with a metadata database, fix a lot of the problems with HDF5. We avoid the problems that ZAR went into, and we make new problems in a new space for ourselves with a new technology. But it'll probably be better. Same, where we pick up, we learn things with the raw data and do interesting and good things, and we get the cloud almost for free. Just almost for free. We get on-prem storage like Deos and these kind of things without being tied into as much Deos-specific technology. Very boring, blobby stuff that we deal with, not hyper-focused stuff on Deos API calls. I think this is doable. I got a lot of requests for this. This may be the next thing I tackle. after my current project I'm working. Thoughts? Got a minute or two? Yes, Harry.
So
That's why Lauren's sitting next to you.
I was just wondering something similar like how different word works with programs, right? So they try to create a structured format with the keys or objects. You could have a 10-dimensional arrays with those keys, and then basically shard the data set, and then you can essentially scan over the data set, kind of repeats itself as graphic formats. You can scan. They typically use things like loom filters to figure out whether the keys exist or not exist there, or
There's awesome.
there's very capability on how this seems very promising. Having looked at it, maybe we had some other issues that same.
No, okay.
It seems a good fit for that.
Take a look at the TensorFlow stuff. Sure.
Yeah, it's basically to look over structures. Structured in a way that you can quickly index into different samples. Read that up. Do the serialized reading, but more randomized shuffling within the memory. So it has a little bit of features around it. They have very capability when.
Okay, all right, cool. Thank you for the pointer. Appreciate it. Elaine?
First, Quincey, we had split driver which separated metadata and whenever did optimization, for example, having the driver brings all metadata into memory, like partial core driver that will really help with big files, but metadata that fits in memory. This is just one observation. Another observation is that when people say that ZAR is faster, you have to ask them really how they use it. And the more speed up they receive from using DAS, right? It's different parallelism, which I'm not saying that HDF5 should work this way, but sometimes we're comparing apple to oranges and trying to push new solutions like this without really understanding the use case and how people want to use HDF5, say, cloud or object store. And already having formats like for HSDS or combining, ZAR with, the same concept, actually having one format for like ZAR and having HDF5, accessing ZAR with all enabling capabilities to aggregate data in different directions from different data sets. This is what the problem people are trying to solve now. And that's where ZAR works well, because you can really combine data in any possible ways, a timeline, a data set. So maybe before jumping into this new proposal, which is kind of okay, store metadata in database, why not? Yes. Really focus on problems that people try to solve and optimize for those problems.
I agree with you, and this is the solution I come up with. Yeah, I understand the problem set, and we can get back just to the split thing. You could tune this all back down to a directory with 2 files in it: dataset data, aggregated dataset data, and a piece of metadata, a file that contains all the metadata. It's exactly the same in the flexible space that I'm talking about for bundles. You can make it be exactly the same, with better probably, than a split file driver is.
Thanks, Quincey. Totally on board. Just a comment. One of the main patterns that people, light sources are falling into is using something like ZAR as the working format, then converting into HDF as an archiving format. So just to keep in mind that we need both functionalities, ideally with the same API.
Yeah, well, that's I'm giving you the same API, right? So it's identical in that way. And I think that we completely avoid the conversion, possibly, right? If we get some traction with this, and we get some confidence with it over a number of years, where we say this works and it works well, and it hits, a set of use cases that's really important, and it is of the same high quality that we have today, why convert? Just take your bundle as perfectly fine. I hope we get there. I'd like to see us avoid the conversion steps and all the extra overhead that involves generally. But, yes. All right.
So Alexander here. So I want to say that, 10 years late has a price, and I think that that's what I'm mostly concerned here. The communities I am operating in, ZAR is so well established. The software tooling exists for ZAR and gets developed and enhanced so quickly that technically, yes, this is a good idea and definitely something worthy. But I think that that really getting noticed when this is done and available is not going to be that impactful. I think that the world in the cloud native way is becoming ZAR dominated, and we just have to, acknowledge that.
I'm not arguing that ZAR doesn't exist and won't continue to exist. I just think we can not cede the battle to ZAR in this space. We could come up with our own technology that is equivalent and better, and let there be a fair competition between something that's native for HDF5 and completely delivered along with it, rather than giving up control of this space to the ZAR committee and whatever they decide. So I understand it's going to be a challenging set of competition to work on technologies that are similar to and compete with ZAR.
Well, you have to win the hearts and minds, and this is where ZAR really benefited from, because people understand JSON, and as far as I know, the most advanced implementation of ZAR is in Python. So Python in JSON is very attractive combination for a layman scientist who wants to kind of feel he's engaged in some way. And I think this was a very winning formula for ZAR, that, hey, you can understand this stuff. And that's something to keep in mind as well.
Yeah, I'm not arguing that. I just don't think it's scalable. I think if you wanted me to go ask, hey, I got this file and it's got 50 million data sets in it, can you tell me what has an attribute named foo? Oh my gosh, how long is that going to take? That query going to go hit the file system to go traverse at least 50 million objects? I mean, these are the kind of things I'm worried about right now. It's how can we exceed what they do right now? Sorry, Jay had something here locally too.
Yeah, no worries.
How complex is the ZAR API as entered by the RT?
I don't know, but it's simpler. Oh, absolutely, sure. Yeah. No, ZAR is not only in Python. There is a very nice C++ implementation that actually is better than the Python implementation.
Although, at least in light sources, we've been having real trouble with it. That is ZAR.
Okay. Yeah, so.
Let's not overstate it. ZAR has a lot of.
All I'm saying is, I just looking at this and thinking, well, we can kill two birds with one stone. We can get to the cloud, we can get to on-prem object stores, and we can legitimately set up a viable competitor in competition against what ZAR's new technologies has uncovered, and be able to compete with them on a native footing. Not giving the battle over. Well, whatever ZAR does is great. We'll just have to deal with it. It takes a minute.
Okay, so we have now part of the Sharding HDF5 file for HSDS. So why don't you use and accelerate existing approaches to read this format?
I'm totally cool with that. It might happen. I have yet to get far enough into this to have a serious enough proposal to be able to talk to John Reedy and Alexander to say, hey, because John was like, oh, this is really interesting. Take a look at the HSDS format for how things are stored in the cloud, and learn and possibly use that. And that's really helpful to have and useful to do. I don't know that the justification for putting it locally. I want to be able to cover the on-prem stuff. I want to be able to have something that runs in a single node doesn't talk to the cloud, right? And that's going to be a lot of work against the HSDS code base. That's almost impossible probably against the HSDS code base. And I wanted to talk to a metadata database and a lot of other things. And I'm not saying it's a bad technology, because it's great technology. It just doesn't do what I need it to do. So let me keep going, otherwise we're so late. Sorry, this is a new deck, and I'm just happy to chat too. So, all right, fine. Yes, someday in the future, we are going to really get multiple processes talking to our metadata, right? Databases can do this. They've been done this for 50, 60 years. My gosh, could we just go use the dumb technology that's already there? And sharding probably makes it a lot easier to go do modifications on the structure and the contents of the data sets in sensible ways. Stupid database can handle all the metadata updates for you. All right, streaming, and I'm going to try to go fast. There's a little less here too, so that's fine. Sorry, I'm going to eat your break, but some of the break I think. All right, why is streaming performance bad? This is fun, right? And the API level for this is very oriented to, really cool HPC stuff, right? Where we're going to access arbitrary subsets on multiple nodes, and we want to make certain that's possible and fast. So we set up the description of the data space in the file. Then we go do the I/O operation where we construct I/O vectors, and we determine the data type conversion. We go get things from the file. We might go type convert on a per element basis, and then we destroy all the selection information, and then we toss it away in memory and all this. When you stick this in the loop, it's terrible, right? It's just amazing. It's especially bad when you're trying to append one record at a time. You're going to go do this every single stupid element. And if you're extending the data set while you're doing this, you put that in the loop too. And you get a whole metadata cycle of things that have to change in the middle of your loop. And if you're storing variable length data, you get an extra bonus, at least one, maybe two, maybe more I/O operations, depending on how nested your variable length elements are that you're trying to store. So it's trying to store a string inside a tight loop like this, where you're appending records onto an end of a data set. It's hard. So this is what the code looks like. Actually, I'm just going to skip this because we're tight on time. All right, there's code. It's probably twice as long and very annoying to go write. Way more detailed, way more API calls than you really need, right? Let's go simplify this. So how do we improve this for streaming? The user tell us. Just tell us what dimension you're appending on, how many elements you're going to give us every single freaking time the time step advances, right? 2 elements. I'm going to give you 2 elements. It's going to be 2 for the next trillion times I call the API. What's the data type of the memory buffer? Set up the stupid memory conversion if you need one, and then do it in bulk rather than every single stupid element you give me in the loop, right? So describe everything up front. Very classic computer science. Let's go extract things out of the loop, right? Set up all this context. Then all we got to do inside the loop is just memcopy. Click, 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 click. Memcopy out of the user's buffer into our own buffer. At the end, we shut everything down because we're good computer scientists. We know how to do this. 4 new API calls. These cover a dozen API calls that you would otherwise have to make. Go set up this thing. I call it cursor. Whatever name. Great name. Somebody has a great name. I couldn't come up with a really awesome name, and databases already have this idea of a cursor advancing through the thing. This is like, fine. I'll use that word. Maybe people will understand it. Better name would be fine with me. So go create your thing that you want to go stream. Tell me this mode operator, right? I'm going to do writes or I'm going to do reads. Here, what axes am I appending on? Because HDF5 allows you to append in different dimensions on the data sets that you create. How many elements are you going to give me at a time? What's the type of the buffer you're going to hand me every time? And anything else special, stuff it in the DXPL or streaming property this, whatever we come up with. And then all you got to do every single time inside your loop is click the button, cursor right, cursor right, cursor right, cursor right, cursor right. It just says memcopy, 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 memcopy until your buffer is big enough that aggregating that off into a type conversion if you needed one, or stuffing it off in the file. Hi, Harry.
Quick one. So how are you? So typically, traditional consumer kind of workflows, which are very nice for streaming. What's the synchronization mechanism? When will the consumer typically look at our events and like count, giving out a publish, and then They'll have a bunch of consumers who could get those events when they do the query, kind of near real time, of course. So the idea I'm trying to figure out is the granularity of when you write something into the buffer, flush it down, and you'll not close the file, and you're trying to read it on the other side. What granularity?
Yeah, when the reader is actually see it, or where is it saved too, right? If you crash, what would happen? So I blazed past that, right? I said, we're gonna aggregate 1 million of these, and you tell me that in your dataset transfer property list, because maybe there's some more knobs and buttons that we want to add on to that, but that's a user controllable thing that says, make certain this gets to disk at least every n elements, and do it like this, whatever other properties, more properties, are relevant to this. Sorry, AJ.
So you're adding for you're assuming something this, so why?
The disk?
Yeah.
No, I don't care what it is. All right, then make your knob say 1. I don't care. What's that?
One of them that's false.
Oh, I probably would, right? But see, the defaults are dangerous, right? Because people will take my default of 1 and then do dumb things with it to a disk and say, wow, that was supposed to be faster. Why is it not faster?
But if you're using this, then we've done it. I will stop right there. So let's take it back. It is a part of the stream side as well as a static file side, but I think that instead of adding APIs, it should be a matter of let's figure out how to get both nodes and recoup the API.
Well, rethinking API, they have data set right, kind of fix it. That kind of behavior that you're stuck with, where it's a one-off, everything happens in this thing, and I don't have much control over making that better. I did make a jersey, 3 where it was, but in order to get the next 3, I need this.
But you can ignore it.
I do what?
You can ignore parameters. You just put the data set in a particular way or parameters. APIs together.
Oh, sure, I get that, but I at least have to look at them because I don't know if this is a streaming write or some of the other kind of writes. I have to examine things, and it's just extra overhead. In order to write, let me just give you a little bit of for this, right? I had a use case where it was as tight of a loop as I could make with today's API. It was getting 7% of the disk bandwidth, of the storage bandwidth. I don't remember what I was going to get. And so I could work with the current API, and I did as many of the optimizations as I could possibly squeeze into the current API. And I got it up to about 30% of the current bandwidth I was getting to disk, right? I could not squeeze more out of that thing. I've already done that optimization. In order to get the next 3x, because our goal has always been try to get to 90% of the underlying storage bandwidth, right? If I got to get another 3x, I am not getting it out of that API. It ain't handy. I already done that. And so the only way I can get out of the current thing is to go something like this. I'm happy to fiddle with it, right? But I can't do it in the current.
I understand the point is that you are saying that you can't put a flag with the open if you're going to and with that hand if you status that's my suggestion.
Maybe. I'm happy to try it, sure. But you gave the magic flag to the data set open that told me to ignore all the other stupid parameters except the buffer and everything is all configured. I'm a little worried that would be really hard for users to understand. And it is not just a go fast flag. It is like a go fast, hairball or something, for them to stumble over.
I'll give you an example of why I think this kind of API is a bad idea. And that is when I was trying to do transaction stuff I did many years ago. I discovered, because I had not really covered the MPI standard, that MPI sent was not being sent.
No.
It's one of the multiple implementations of things. And that's kind of the situation here where it's saying, oh, I have a whole separate API that I have to use in this case. Rather than, I want to change the way that I do stuff and all my various calls. That's where a lot of this complexity is coming in. So rather than multiplying out the number of API calls, finding ways to collapse that and use a standard set, deals with a lot of the complexity. Because as you usually come in and say, well, there's 4 versions of reading a file, which one do I do?
No, I get it. I've been on the API committee now for 20 years, and I get it. I know, but you wanted the simpler APIs, man. Sure. Well, here's 4 of them. I don't know. I'm happy to keep talking, but I'm getting people's brains.
This is we could 5 minutes into the break.
I know, right? You want me to just? Well, I'm happy to chat later too. Let me scroll through this and see if there's anything really, really critical that we got to hit. We gotta go fix the storage too, because the way the storage works now, with the way the chunks and indices work, is terrible, tragic, and it won't. What we have today is never going to achieve the speeds that we need from variable length strings and other things that we want to put in the file, and it's particularly also suboptimal, although not completely tragic, for fixed size appends and going off of there. So you don't get my magic slides about data structures. You'll have to talk to me or read them online. Thank you for the great discussion. Sorry I stole 5 or 10 minutes of your break. I hope you enjoyed it.
Hi, this is Marquis Optical. I was wondering if you had any thoughts on checksums.
Checksums on at least metadata are required to the level that I cannot stress enough. And I seriously believe, based on the learnings I made this earlier, fixing all the CVEs last year, they should be on by default for raw data as well, and out with a lot of really bad warnings saying don't do this on raw data.
And so I'm wondering if you've ever considered using something else other than Jenkins Lookup 3.
Oh yeah, I don't care the algorithm, there's got to be just required to. Almost everything on the CVE yesterday was, but not yesterday, last year was fundamentally based in the fact that there was no checksum.
And so that's,
They're playing with a mic, and I don't know if you can still hear.
I just like throw it into Word, so.
Okay, all right.
I don't have.
We can chat, Mark. Happy to do that, but it might be challenging.
Yeah, no problem. You can chat offline. Thanks.